Alright, hi, it's Megan, and this is video problem 5. So for the first question, part A, we know that Uncle Kramer's house, W, is located at 2571 in the standard basis. So we can go ahead and write that as a linear combination right here, where the vector W equals some constant A times vector V1 plus B times vector V2, where these are our direction vectors. V1 and V2 are the direction vectors given by the new travel basis, and this vector W is the vector that we're given in the original standard basis, and then this is just like the amount of time you have to travel on each vector to get to this one, which is what we've been doing for a long time with the linear combinations, but that's just another way to interpret the standard basis and the new basis. So you can see these vectors come from the beta basis. So I went ahead and set up that linear combination right here, and then went and solved out the vector equations to get negative 4.2 and 37.6 to be A and B, and those A and B values represent the vector in the new coordinate system. So we could go ahead and name that beta. So that's part A, and for part B, we're trying to answer, we're trying to convert a vector in the beta basis into the standard coordinate system. So we're given that the new basis, we also know that the standard coordinate system is going to be 1, 0, 0, 1, and we're given this new vector in the beta basis is 8, 3, and we're trying to name it to alpha basis. And we're given the basis for the beta basis, which, if we looked at this diagram right here, represents the P transformation. So P renames the beta basis into the alpha basis. So if we're given this vector right here in our diagram, if we wanted to get this vector, we're going to apply P. So I went ahead and applied P right here times the given vector. It's going to equal 2714 in the alpha matrix. So the original alpha basis, the original coordinate system. Okay, there we go. And for part C, I'm going to use a more geometric or graphical representation of the same thing to rename some coordinates. So the black lines are going to represent the standard coordinate system, and these red lines, I didn't really continue it all the way out, but these lines would be continued here, 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 and here to form the new basis. But again, it's just looking for a linear combination of these, like a pathway on these vectors to get to this point in the standard basis is going to correlate to the vector in our new beta basis. So we're given the vectors in alpha basis. Those are the blue dots right here. Those are those coordinates. And so I just looked for combination that's going to get there. So it's going to take 1, 2, 3 of the 3, 1 vector, 3, 1 travel vector, and 2 of the negative 2 of the 1, 2 vector to get to this spot. So the new U1 vector U1 in the beta basis is going to be 3, negative 2, and you can see it checks out if we do it just like the linear combination style too. And then for U2, which is negative 6, 3. Sorry, the graph kind of goes off the page, but it's going to take negative 3 of the 3, 1 vector, and then positive 2 of the 1, 2 vector to get to the new spot. So, just like the linear combination, U2 in the beta basis is going to be negative 3, 3. And again, double checked it with the linear combination. Alright, and for D, expressing each of the following in terms of the standard basis, given these two vectors in the beta basis. So, like we said before, this is going to this matrix P, we called it in the previous problem, 3, 1, 1, 2, is going to rename the beta basis to the alpha basis. And the way we're going to do that is just then multiply that renaming basis times the vectors that were given to get these vectors, which are the answer in the standard basis. So Z1 is 25 in the alpha basis, and Z2 is negative 15, 0 in the alpha basis.